Welcome back. We are at the last leg of module number 10, Introduction to Neurophotonics, and today's lecture I am going to keep it short. This will be more or less a revision, and we will be discussing mostly about the tomographic technique. We have discussed and you have learnt about optical coherence tomography. So, there is a specialized type of tomography that we use, and the principles more or less will remain same. There is slight difference between OCT, but today we are going to discuss this tomographic technique for brain imaging. So, what we actually mean is that tomography is a medical imaging technique that involves creating cross sectional images or slices or object of the body. You know CT scan, coherence tomography. Previously you used to have X-ray just in front of you and they will take a image of your skeleton, but CT scan is where the X-ray is having a 360-degree view of your entire body, and thereby it takes a full 360-degree X-ray image. So, tomography is something similar. Well, it is CT scan, the T of CT scan stands for tomography, coherence tomography. So, tomography is a medical imaging technique that involves creating cross sectional images or slices of the object or a body. So, you have the targeted object from different areas. It is used to visualize internal structure in a non-invasive manner. Tomography provides a three-dimensional view of the object by capturing multiple images from different angles and then reconstructing a detailed image of the internal structure. So, you are having a X-ray from here, X-ray from here, X-ray from here, X-ray from here, and then you reconstruct a three-dimensional. I am using the term X-ray because CT scan is something probably all of you have heard of, but computerized tomography, but we use something similar with brain and obviously not with X-rays. X-rays will most definitely fry up the brain. So, you use basically the non-ionizing radiation method, the radiation that is absorbable or transmittable depending on what we are looking for. So, the limitation of the traditional methods is simply this: positron emission tomography uses ionizing radiation, which limits its use in children. Ionizing radiation can have potential long-term health effects, especially in young individuals. Functional MRI, magnetic resonance imaging, involves strong magnetic fields and electric fields, making it unsuitable for patients with implanted electronic devices. At the same time, fMRI do not have that much of a resolution. I have been telling you they do not have this much of a resolution. This is PET, positron emission tomography, where we use obviously a positron. You know what a positron is, medical students? You should know what a positron is. You know electron, right? Think of a positive electron, positron. So, anyway, this can have high resolution, but fMRI, functional magnetic resonance imaging, has low resolution, and it is unsuitable to use this technique for patients with implanted electronic devices such as pacemaker, deep brain stimulators or cochlear implants. Even if you have a hearing aid associated with it, or internal some hearing aids implants are actually inside, which helps if you have internal damage, then you obviously cannot use high strong magnetic and electric fields, right. So, what are the advantages of DOT? DOT is a specific type of OCT, diffused optical tomography, or DOT imaging. DOT uses functional near infrared spectroscopy. We have discussed NIRS, near infrared spectroscopy. Here imagine the same thing, NIRS, at all different slices, different angles, and then reconstructing it. We have discussed NIRS, right. So, DOT uses functional near infrared spectroscopy. It offers a safe alternative for brain mapping. FNIRS utilizes near infrared light, a low energy form of light, to measure changes in blood volume and oxygenation of the brain. You already know this. The technique is safe and non-invasive, making it suitable for various populations including children and patients with implanted electronic devices. FNIRS utilizes near infrared light, low energy form of light, and the technique is safe and non-invasive. I think she has repeated the same thing twice. Okay. So, high resolution dot. So, diffused optical tomography is an imaging technique that utilizes NIRS. As light travels through tissue, it undergoes scattering due to interaction with cellular structure and other components. This scattering causes light to change direction and intensity as it propagates. Different tissues have distinct optical properties, i.e., different tissues will scatter differently, different tissues will have because of the scattering, because of the change in refractive index, different absorption profile, the light will be, photon will be going in a different direction, and from that you can calculate, you can back calculate what type of tissue, what type of functions it is there, and thereby reconstruct a 3-dimensional working image of the brain, while the animal or the human being is still alive, you do not open it up. So, different tissues have distinct optical properties related to light absorption and scattering. These properties are influenced by factors such as concentration of chromophores, if you have tagged it, or the size of cellular structure. Hemoglobin and water are common chromophores in biological tissues. These are endogenous or exogenous? Endogenous. Oxygenated and deoxygenated hemoglobin had different absorption properties in near infrared image, and you slice it through. Yes, hemoglobin is not necessarily always going to be present inside the brain. We discussed about the blood brain barrier, but you can always use water. You can talk about cerebrospinal fluid for spine, of course. You can also use the brain fluid. So, all of those things. So, instead of just having one direction, you send different types of NIR light and then try to reconstruct a 3-dimensional image. So, this is the overall, fiber optic array for detection of breast cancer, which, so dot is not specifically for brain only. This can be utilized for other type of diseases as well. Here you have it's for breast cancer detection. So, high resolution dot. In dot, multiple light sources emit near infrared light into the tissue. Multiple light sources emit near infrared light into the tissue in different direction, and detector plates on the tissue surface measure the diffused reflected light. The intensity and distribution of the reflected light are measured at various source detected pairs. Various computational algorithms are used to reconstruct 3-dimensional maps, and these algorithm aims to find the best fit between predicted and measured light intensities, right. So, yes, if near infrared spectroscopy deals mostly with hemoglobin, oxygenated or non-oxygenated blood, but you can also tag and thereby make other fluorophores absorb a particular light which otherwise is non-absorbable by brain, but then you are also trying to look into the output, a wavelength which may or may not also be absorbed by the brain. So, overall, like any other tomography, different angles, different slices, the output is also coming from different angles. You collect all of them and then you reconstruct the overall brain. So, several application monitoring brain functions and activation patterns during cognitive task, investigating brain disorder like Alzheimer's disease, studying brain development in infants and young children. It has also found application in cancer detection, oncology, detection and characterization of tumors in breast, brain and other tissue, monitoring tumor response to treatment like chemotherapy, guiding surgical procedures by identifying tumors, margins and critical structures, imaging breast tissues for early detection and characterization of breast cancer. Cardiovascular imaging, musculoskeletal research, functional connectivity studies, all of these have used FNIRS simply because the light is non-ionizing, Usually brain tissue do not absorb it, so you can pass it through, but hemoglobin absorbs it. So the distribution of capillary, distribution of veins, distribution of arteries, all of those things can usually be measured, and a 3-dimensional map could be created. Now, how is DOT? Diffused optical tomography different from your normal optical coherence tomography? I know this question will come. So, obviously optical coherence tomography is the overall set, DOT is a subset, and different types of OCT. There are several different types of OCT. One of them happen to be DOT. There are other DOT, time domain OCT or spectral domain OCT or swift source OCT, Doppler OCT. We have discussed this, remember the blood clot, angiography OCT. It is designed to visualize blood vessels, particularly used in ophthalmology. Spectral domain employs a spectrometer to simultaneously measure the interference signal. So, DOT, diffuse optical tomography, is a part of optical coherence tomography, but optical coherence tomography and DOT has some very specific differences. Now, this is the image that you already know. I have shown you. This is the OCT of the fingertip. You can see the sweat glands, the corkscrew appearances. These are the sweat glands, and then this is the map of the thickness of the eye. This is of breast cancer, I think, of sarcoma, and this is the macular area of the retina. But well, OCT also has several applications in like glaucoma, retinal detection, neurodegenerative diseases, optical neuritis, multiple sclerosis, MS. But let's see, these are several other applications which I have given for you to read in your own spare time. But what is the difference between DOT and OCT? Right. DOT uses near infrared light to measure changes in the absorption and scattering of light with biological tissues, whereas OCT is low coherence interferometry and uses near infrared light to generate high resolution cross sectional images. So, understand the difference. This near infrared is simply to penetrate through. DOT mainly uses to create a 3D map of tissue properties. OCT provides detailed structural information. There will be several overlaps, of course. OCT is excellent for imaging superficial tissues and visualizing tissue layers and structure. DOT is particularly suitable for studying deeper tissue. Both are similar techniques. OCT is mostly the top periphery, DOT is inside, but then you have seen in previous images that OCT is also giving you information from the depth of the tissue. So, for all intent and purpose, DOT is a type of OCT. Yeah, DOT is a type of OCT. DOT provides a functional information, but generally have lower spatial resolution compared to OCT. Absorption may occur, whereas OCT offers high resolution structural imaging. Resolution is typically in the range of few millimeters to centimeters in DOT, whereas OCT can produce cellular structure with fine tissue images. DOT provides information about tissue function and properties, where OCT emphasizes mostly on the structural part. One gives you more information on the structure, but DOT, which is another specialized type of OCT, gives you information on the tissue function and property. So, I think that is enough for brain imaging that we need to know. There are other, obviously this is not an exhaustive list, there are several other topics on the how to image brain. I have tried to cover some of the main ones. Under no circumstances they are the most important or they produce the best results. They are for the time being producing enough information so that we should be interested to look into it. It does not mean that any of this is best or better, or it produces, all are complementary to one another, all are complementary to one another, and maybe in future several new types of microscopy techniques will come up, which we will be able to use and detect the brain in real time, i.e. how the neurons are functioning at a femtosecond, picosecond pulse, how each neuron is talking with another neuron, a particular function is performed. We are still quite a far away from mapping that, the functioning brain mapping that needs to be discussed, that needs to be ascertained, that needs to come at a later stage. So, DOT has the ability to penetrate deeper tissues, it's less harmful, and not just in brain, it is used in ophthalmology, cardiology, dermatology, skin, heart, eyes, and it also helps in diagnosing, monitoring conditions like glaucoma, problem in the eye, retinal disorder, vascular health, and skin diseases. So, these are the topics that got covered today, and these are my references, and thank you very much. I will see you with a new topic.